watch the completion of squares, Natalie, I want to show you some math magician stuff. It's clear that this is true, right? That 7 plus 3 is equal to 10. Do you agree? 7 plus 3 is equal to 10. And you had some questions about this equal sign, so we might as well go through it. Anything I do to the left side of the equation, if I do it to the right, will stay balanced. For instance, this is true too, isn't it? I subtracted 4, and then I added 4, which is pretty much 0, isn't it? But let's make sure. What's 7 plus 3? It's 10. What's 10 minus 4? It's 6. What's 6 plus 4? It's 10. And on the right side, it's still just 10. Equals 10, right? Nothing sorry, equals 10. So just by subtracting 4 and plus 4, it's obvious that little step is still just 0. But it's interesting because we will need this trick for manipulation of completing the square. Let's keep going though. Pretend I added 4 to this side and added 4 to this side. Whatever I did to the left side, I did to the right side. Well, it's clear that 7 plus 3 plus 4 is 14. And it's clear on the right side that 10 plus 4 is 14. So you can still see I got the same answer as when I started with 7 plus 3 is equal to 10. Which means I can add anything to the right side. For instance, I can add the square root of 2 to the right side and add square root of 2 to the left, to the left side, and then add square root of 2 to the right side. And I will get the same thing. To prove this, it's clear that this is just 10 on the left plus the square root of 2 and 10 plus the square root of 2 on the right side. That's what equals is. If you have the same on the left as you do on the right, then they are indeed equal. Well, that means I can do all sorts of manipulation, and it's important to understand that I can even add things like 2x to both sides of an equation, and they will still be balanced. So this 7 was a 7 plus 3. I added 2x to this side and 2x to this side. But note that I don't have to add it to the right side. I can also just add it and subtract it to the left side. It's essentially 0 there, isn't it? And you might say, why would I ever do that, Peter? Well, if you start getting into perfect squares, this, for instance, is the same as x plus 3 squared. Okay? And to prove it yourself, just do x plus 3 times x plus 3. That's what x plus 3 squared is. Foil it. Get x squared plus 3x plus 3x plus 9. Add those middle ones terms together because they're terms in common, and you get this over here. So that means this is true. But sometimes you see in the vector format, which is what we're using the completed square for, we want this, but we don't ever always have the perfect 9 over here. Let's suppose I only had a 3 here. Well, I know that's not true anymore. So this is not true. But if there was a way I could add 6 to this left side and 6 to this right side, it suddenly is true, isn't it? So all I did was, oh, actually I have to be careful. All I did was add 6 here, right? But if I add 6, I have to subtract 6. Okay, what's this first part here? Well, that's the same as plus 9, isn't it? And we've already learned that this part here is the same as x plus 3 squared, isn't it? We've got to keep the minus 6 here that we added, which means it's the same as our expansion, minus 6. Or sorry, this was minus 6 is this. That's what we started with, right? You can go ahead and foil this and then subtract 6, and you will discover that this is true. That means we can manipulate things that aren't perfect squares to achieve our perfect square. And this, by the way, is vector format. The vector of this parabola is minus 3 comma minus 6, the opposite of this, and the exact value of this. That's the y, and that's the x. So that means if I find myself in a situation like this, and I know it's not a perfect square, I can just say, wait, Peter taught me that this is the same as thing. I have not changed this equation on the left because I added a 6 and I subtracted a 6. Now I can just focus on adding these 2 points, which make 9. And boom, I've created my perfect square and I haven't changed the equation. All I did was subtract 6. So I get this. And that's going to be the same as x squared plus 6x plus 3. So you can see I kind of manipulate. I've added numbers to create my perfect square into this situation. It gets more complicated when there's a number in front of x squared, but that's what the next video is. I want you to be very aware of this mathematician trick because you can do it endlessly. You can add all sorts of things to the left and right side of the equation, or 7 plus 3 is equal to 10. But this is true. Still equal to 10. And this is true. I can keep going on forever. I can add anything I want. I can add this 2x, and then I can add 3x squared, so long as I add it to the other side. And this is still going to be equal to 10 because these will cancel out on both sides. And these will cancel out on both sides. And I'm left with that. So whether I add it and subtract it to one side, that's still true. Or I can add it to both sides. You'll find that both are useful. Adding and subtracting this side, it's very clear to see that this is just 0. I've just manipulated 0 into a magical form. And we use it for completing the square. Hope that helps. Be aware numbers are just fantasies. They're imagination, and you can manipulate them any way you need to achieve your goal. That's what math is.